Welcome back to the deep dive, where we crack open the most complex research and, well, give you the knowledge shortcut. Today, we're talking about speed. But not just the speed of light, we're talking about the speed limit of glass.
Right.
Conventional fiber optic cables, the foundation of our entire internet, are solid core fiber, or SCF. And they are getting really, really close to their theoretical limits.
We're basically bumping up against the physical laws of silica itself.
Exactly.
And that's why this deep dive is all about hollow core fiber, or HCF.
Yeah.
This technology, it completely resets the race. Instead of trying to squeeze more out of solid glass, HCF guides light through an air or gas core.
A hollow core.
Yep. And the most advanced design we're seeing right now is called nested anti-resonant nodeless fiber. NNF for short. It's just a really elegant solution designed to get around those limitations of glass.
Okay, so that's our mission today. We're going to dive into the sources we've got, understand the genius of this HCF structure, and look at the performance metrics that are setting, global records.
But also, and this is critical, the massive engineering hurdles.
Oh, yeah. Splicing, testing, all the practical stuff that has to be solved before this super fast cable can become a global standard. So let's start with the big question. Why air? What are the, say, three main advantages HCF has over traditional single-mode fiber?
The switch from glass to air is the medium. I mean, that's the key to everything. It unlocks performance gains that were just unimaginable before. And yeah, it really boils down to three big benefits.
Okay.
The first, and this is the one that gets all the headlines, is ultra-low latency. Light just travels faster in air, almost 32% faster than in a silica glass core.
32%.
Yeah. If you look at the refractive index of glass, it's about 1.468. The air core in NNF, its effective index, is just 1.003.
And that 32% isn't just some technical detail, right? For anyone in, say, finance or cloud computing, that's a huge deal.
It's enormous.
What does that actually mean in terms of raw speed savings?
Well, that difference translates directly to a latency reduction of about 1.53 microseconds per kilometer.
Wow.
So over the thousands of kilometers linking cities, those microseconds, they stack up into milliseconds. And that could be the difference between profit and loss for, high-frequency traders.
Okay, so that's speed. What's the second big win?
The second is negligible optical nonlinearity. In standard fiber, the light is really interacting with the glass, which creates all these annoying side effects, the Kerr effect, Raman scattering. They basically mess up your signal at high power.
They degrade the signal.
Exactly. But because HCF keeps the light in the air away from the glass, these nonlinear effects are reduced by 3 to 4 orders of magnitude.
3 to 4 orders of magnitude.
I mean, in some of these NNF designs, the Kerr nonlinearity can be 10,000 times lower than in standard fiber.
10,000 times. So if the signal is that much cleaner, what's the bottleneck now? Can we just crank the power up indefinitely?
Well, that brings us right to the third advantage, high power handling. Because there's so little interaction with the silica, thermal issues are drastically reduced. The fiber's damage threshold is way, way higher.
So conventional fiber just melts.
It can, yeah. You pump too much optical power through it, the glass melts or cracks. But with HCF, since the light is mostly in the air, you can transmit far, far higher power levels.
Okay, so speed, signal purity, and power. But we have to talk about loss. Conventional SMF is the gold standard of efficiency, isn't it? It's already incredibly good.
It is. The benchmark for conventional SMF at the 1550 nanometer wavelength, you're looking at loss limits around 0.14 to 0.16 decibels per kilometer. And that's an incredibly tough number to beat. It's set by the intrinsic material limits of silica itself.
Right. For years, HCF had terrible loss figures. That was the showstopper.
It was.
So how does HCF, with this complex, thin structure, how does it stack up against that benchmark today? Are they catching up?
They're not just catching up. They're starting to surpass it. Through just relentless refinement of the design, losses have come down dramatically. We're now seeing documented lab prototypes of HCF with losses as low as 0.11 decibels per kilometer.
Wait, 0.11. That means they could be operating below the theoretical limit of the best solid glass fiber. That completely flips the script.
It does. We're using air to beat the fundamental loss limit of glass.
Okay, this is where it gets really interesting. Let's talk about that structure. In traditional fiber, we use total internal reflection, right? Light bounces off the boundary between a high index core and a low index cladding. Air has an incredibly low index. So how on earth do you keep light confined to an air core?
The physics is based on something called the anti-resonant reflecting optical waveguide principle.
Yeah?
ROW. So you're not using simple reflection, you're using wave interference. Think of it like an incredibly precise filter.
A filter. Okay, break that down for us. What's the difference between resonance and anti-resonance here?
Okay, so imagine the super thin glass walls of the capillaries around the air core.
Yeah.
At certain wavelengths, the resonant ones, those walls are basically transparent to the light. It just leaks right out. Loss is extremely high.
Oh.
But by carefully designing the wall thickness, and we're talking less than half a micrometer sometimes, engineers tune the fiber to operate between those resonances. In that anti-resonance state, the light is forced to reflect back into the air core. Confinement is maximized, leakage is minimized.
So the geometry of the walls is everything. It's a selective mirror, essentially.
Precisely. And the NANF architecture, that nested anti-resonant nodeless fiber, that's really the peak of this evolution. Earlier designs like photonic bandgap fibers were just too complex and hard to manufacture.
And what makes NNF so much better?
It uses multiple nested, thin-walled tubes. But crucially, the nodeless part means those internal capillaries don't touch each other.
And why is getting rid of those contact points so important?
Because those contact points, the nodes, were major sources of scattering loss in older designs. Getting rid of them, making it nodeless, that was the massive breakthrough that dropped the loss so dramatically.
That technical precision is translating into some pretty incredible real-world performance. Let's pivot from data to just pure energy. This technology isn't just about faster internet, it's about delivering raw laser power.
Oh, absolutely. This is a game-changing milestone. Researchers recently demonstrated the first all-fiber delivery of a 2-kilowatt laser.
2 kilowatts.
2 kilowatts over a distance of 2.45 kilometers. Using a self-fabricated HCF, this moves it squarely into the industrial world.
2 kilowatts over nearly 2.5 kilometers. We've gone from sending, a gentle stream of data to basically using this fiber as a fire hose for industrial lasers. What kind of efficiency did they get?
It was impressive, 85.4% transmission efficiency. And the fiber itself had a very low loss of 0.168 dBs per kilometer at the 1080 nanometer wavelength they were using.
So when they pushed that much energy through, did they find a new problem? Was the fiber itself the limit, or did something else pop up?
That's a great question. Pushing limits always uncovers something new, and they did. They observed stimulated Raman scattering SRS being amplified. But here's the interesting part. Not in the air core. It was happening inside the silicon-nested tubes.
So the problem wasn't the fiber's capacity, it was the purity of the laser going in.
Exactly. The solution wasn't to fix the fiber, it was to clean up the source. They used a special kind of filter, a chirped and tilted Bragg grating, to clean up the Raman noise from the laser before it even got into the fiber.
This high power capability is obviously useful for heady industry, things like laser cutting. But the sources mention some even more critical remote applications.
Yes. Think about hazardous environments. This enables things like subsurface laser drilling in oil and gas fields, but maybe even more important is its potential for nuclear decommissioning.
How so?
You can use a remote, powerful laser to do the work. It dramatically reduces the time that human workers have to spend exposed to radiation. It's a huge safety improvement.
It sounds like we've solved half the equation. We have unmatched performance in speed, purity, and power. But physics usually demands a trade-off. What's the reality check here? If HCF is so revolutionary, why isn't it everywhere already?
This is where we hit the wall of its inherent fragility and complexity. The number one problem is splicing, joining two fibers together.
Right.
Those thin quartz walls of the nested tubes, they're often as thin as 0.4 micrometers. When you use traditional fusion splicing, which uses a lot of heat, those delicate structures just collapse, they deform.
So just connecting two pieces of cable in the field, which has to happen all the time, becomes this incredibly delicate procedure. Are they finding ways around that?
They are. The research has focused on ultra-low heat techniques, using really optimized minimal discharge parameters. Think 20 milliamps of current for only 600 milliseconds.
Just enough to fuse, but not enough to melt the structure.
Right. And they also use special anti-reflection coatings on the end of the solid fiber they're connecting to. That helps mitigate something called Fresnel reflection, which can cause a 4% power loss just from the air-to-glass mismatch.
And with all that, what kind of splice loss are they getting?
With those optimized methods, they've gotten it down to a pretty low average of about 0.17 dB.
That's pretty good for such a difficult splice, but I imagine the structure still needs mechanical protection.
Absolutely. So that's led to more advanced solutions like embedded splicing. One method uses a tapered borosilicate glass tube as a kind of embedded bridge or sleeve. It protects the structure during the process and has shown promisingly low insertion loss, about 0.6 dB for a whole link.
Okay, now for a problem that seems completely unique to this technology, the measurement problem. When you lay cable, you have to be able to test it, right? Find breaks, check the loss, usually with an OTDR.
An optical time domain resectometer, yep. And it relies on light bouncing back from the fiber
Except
material.
there's no material.
And that's exactly why traditional OTDR is almost useless here. It relies on detecting Rayleigh backscattering, the tiny amount of light scattered back by the glass. Since HCF guides light almost entirely in air, there's nothing there to scatter the light back.
How much is a drop-off are we talking about?
The backscattering signal is up to 40 dBs lower than in standard fiber. That drop is so huge, it basically kills the ability of standard field instruments to see anything useful.
So if you can't find a break in the field with your standard tools, how do you manage a network?
Right now it's tricky. During manufacturing, they use very precise winding meters for the initial length. In the field, they're looking at more advanced things like optical frequency domain reflectometry, or OFDR. The most common workaround is to just fuse solid fiber pigtails onto both ends of the HCF.
And that lets the OTDR test the connections, but I'm guessing there's a big limitation.
The limitation is that it only confirms the connection exists. It can't tell you the exact length or the uniformity of the loss or pinpoint a break somewhere in the middle of a kilometer-long HCF segment. It's a major maintenance blind spot.
Okay, and let's talk long-term. Durability, environmental risk. That fragile inner structure with a hollow core that has to create huge challenges over a multi-decade service life.
It does. And the fragility is really twofold. First, mechanical strength. The thin-nested tubes mean the theoretical fracture strength of HCF is at least 10 times smaller than conventional fiber. It's just much more sensitive to being crushed or bent.
And the second part.
The second, and this is maybe the more insidious one, is moisture ingress.
Water.
Water vapor. The air core is connected to the environment, so moisture can get in.
Yeah.
And once it's in, it forms this light-absorbing film. It accelerates hydrolysis, the chemical breakdown of the silica, and it just dramatically increases the light loss, especially at that critical 1,364 nanometer water absorption peak.
So a tiny crack, a slightly imperfect splice, and the performance just plummets.
Yes. Water vapor is the #1 enemy of HCF durability. It forces operators to go to extraordinary lengths to keep that internal environment pure and dry.
So given all these challenges, fragility, splicing, moisture, who is actually willing to use this right now?
Well, deployment is pretty much limited to fields where that latency advantage is a massive, massive competitive edge. The prime use case right now is high-speed trading, HST.
In finance, where speed is literally money.
Exactly. And we have real-world proof. A field trial in Madrid earlier this year confirmed it. They showed a round-trip latency reduction of 4.2287 microseconds over a 1.386 kilometer link. That confirms the promised 30% latency improvement.
Okay, so a niche where you spend a premium to gain milliseconds. Where else is this playing out in a big way?
Data centers. Low latency is critical for data center interconnects, DCI, and we have a huge commercial signal here. Microsoft acquired the HCF pioneer Luminicity back in 2022.
I remember that.
And they've announced plans to deploy an astonishing 15,000 kilometers of hollow core fiber within 24 months.
15,000 kilometers. Okay, that's not a test anymore. That's a serious commercial commitment.
It's a huge validation of the technology despite all the challenges.
So looking ahead, what's needed for this to go from niche to mainstream?
We need infrastructure reform, really. New, unified product standards. Specialized test methods, since the old ones like OTDR don't work. But the biggest practical hurdle is maintenance. We need specialized field tools.
Like what?
High-power OTDRs that can actually detect that faint signal. And critically, portable bottles of pure, dry, gas like argon or nitrogen, so you can go out and purge contaminated fibers in the field.
That feels like something out of science fiction compared to maintaining normal fiber.
It is. But purging a fiber is a lot cheaper than replacing an entire cable segment just because a little moisture got in. It's a whole new layer of complexity for network maintenance.
And what about future capacity? Can it handle the kind of data loads we're expecting?
Actually, it shows immense promise there. Because of its low dispersion and incredibly wide bandwidth, it's great for dense wavelength division multiplexing, or DWDM. Experiments have already shown aggregate data rates up to 38.4 terabits per second over short distances. So the capacity potential is definitely there. So we've taken the deep dive, and I think the core significance is this. HCF, and especially this NANF design, it isn't an incremental update. It's a radical shift that leverages the innate speed of error to push performance far beyond the physical limits of glass itself.
It's really a study in contrast, isn't it? On one side, you have this unmatched speed, this ultra-low nonlinear multi-kilowatt power handling, and on the other, you have this hyper-fragility, this incredible difficulty in splicing, and this constant threat from a single molecule of water vapor.
That's the trade-off.
Which brings us to our final provocative thought for you to chew on. We've established that in theory, optimized hollow core fiber could get to attenuation losses near 0.001 dBb per kilometer, a loss so low no silica fiber could ever touch it. But given that its entire operating life can be ruined by a single molecule of water vapor leaking in, what's the trade-off threshold? When does the immense speed advantage of air become worth the hyperfragility of its structure? When does that need for absolute purity become the new speed limit?